error-bound formulas in section 6.2 is what we want to talk about. And on page 387, you can see them. There they are, right at the top of page 387. Those are the error-bound formulas we're going to talk about. Okay, now when we talk about error-bound, what we mean is max error. Max error. Okay, what's the most error that 20 left rectangles could have? Okay, so let's take an example of, say, this problem right here. Let's just do the integral from 0 to 2 of sine of x squared dx. And we wanted to know what is the max error that 20 left rectangles would have. So that would be something that looks like this. Okay, that's the question. And then, you know, is there a number out there that we know for this integral? Because we don't know the antiderivative of this integral. So we don't know the exact answer. Yes, our calculator could give it to us. We'll do that in a second. But how does a calculator know? How does a calculator give us that exact answer when there's no antiderivative? That's our real goal today. How do the programmers that wrote the code to have the calculator give us that? How did the calculator? How did they know that it was 20 decimal places accurate or 15 decimal places accurate or whatever? How did they know that? All right, and then we'll talk about what about midpoint and trapezoid, because they're a little different. Okay, how much error? What's the max error for 20 midpoint rectangles to this thing? Okay, and how many rectangles would it take to guarantee us 6 decimal place accuracy or whatever, right, based on this? That's our goal today, is to come up with these formulas. Now, when we're done with it, I mean, I think it's important for you to see it and think about it and see where it comes from. But in the end, you're not going to have to do that for the quiz, and you're not even going to have to memorize those formulas. Okay, what the pieces are you need to know, but I will give you those formulas on the quiz. All right, so if you go into your, we'll call this I, call the integral I here, and on your calculator there, Wyatt or everybody, go ahead and just type that in, that particular in. Okay? Sine of x squared from 0 to 2. .805. Okay, so we know the exact answer is 0.805. All right, so talk about the left rectangles first. How much error, what's the most error there could be with left rectangles? Well, to do that, we have to start with what causes the error. So what causes a left rectangle to be off? If the function what? Increases or decreases. And what's the most, and what determines how much it's off? The slope, right? We already talked about that. Okay, so what if we had a function, I don't know what this function looks like, and we're going to just pretend, you know, whatever, we had a function that did this, okay? And I'm going to make it easy, I'm going to make it go through 0. And so, oh, okay. All right. So, so if we go through the origin here, and what if we did this? Again, what we want is the max error, the worst case scenario. We want a number that we know the error is not more than that, guaranteed. Right? I've got $10 million or less in my pocket. Right? That is a number guaranteed. The most money I have in my pocket, okay? Probably not even, it might even be close to the actual amount of error, but guaranteed to be the most. So what if we did this? What if we took where this graph was the steepest, maybe right there, I don't know. What if we found, and of course we could get that by doing what? Derivative, right? What if we found in our interval, and we're to make it easy on ourselves, we're only going to look at one sub-interval. We'll go from 0 to h. or delta x, you could call it, but we'll use h because that's what the book uses. Let's just use one subinterval. We might be going all the way from A to B here, right? We might be looking at this whole interval, but let's just say, let's just look at one subinterval, and let's say what's the steepest the graph ever is. And let's pretend that the graph had that steepness the whole time. Does that make sense? That would be your worst case scenario. Because the most it'll be off is if the graph is the steepest. Right? So let's find where it's the steepest and pretend it had that steepness the whole time. So here's what we're going to do. We're going to call K1, we're going to call that number K1. K1 is going to be the max of f prime. Right? The max of f prime. Now, of course, we know how to find a max, list of candidates, do all that. I'm not going to make you do all that. We're going to cheat. We're going to use a calculator. Okay? So, the max, we're going to call it K1, the max of f prime, the steepest the slope ever is. And we don't care if it's steep going up or steep going down, right? One way it's over, one way it's under. So the way we're going to do that is we're going to put bars around that. So we're only going to care about positive slope necessarily. If the slope's negative, we just put bars around it, okay? All right, so if the steepest happened to be when it was going down, we would use that number instead. Right? So if the steepest slope was negative 3.8, we would use 3.8 as our K1. Okay? All right, that's going to be an important number for us to use. Now, what we want to do next is we want to pretend that f of x, was a graph that had K1 as its slope all the time. What would be an equation of a graph that had K1 as its slope all the time? K1 times x. Well, right. We don't know the y. That's what we're going to pretend it goes through the origin. Okay, so this is f, so we won't worry about any vertical shift. Wouldn't it be, well, think of it this way. If you had a graph where f prime was K1 the whole time, then f would be the antiderivative of that, which would be K1 times x plus some c, but we'll ignore the plus c. So it'd be K1x. So we're going to pretend that this function is K1 times x the whole time. And remember, K1 is the steepest slope. So clearly it's not going to be. Now, if you want to look at a picture on 390, they have a picture on 390 where they kind of do this same thing that we're doing right here a little bit. They show you a picture of a blue graph there at the bottom of page 390. They show you a picture of a blue graph and they say this is our graph and let's find the steepest slope called that K1 and then let's pretend it follows that the whole time. So what we're going to find, so what we want to find is the amount of error. We want to find how much error is between a left rectangle and that function right there. Okay? Well, first of all, to get the area, and we're just going to do one subinterval to make it easy, and then we'll find the amount of error in one subinterval. We'll multiply that by n, because there'll be that many subintervals, okay? And then 20, and then we'll come back and deal with the 20 here in a minute, okay? So, the exact area, if this graph actually had this as its curve the whole time, right? We're going to pretend that the curve actually does that, right? It has that amount of steepness the whole time. So it would be the area from 0 to h, and here would be the function K1x dx, right? Okay, so what would that be? What would be the antiderivative of K1x? K1 is just a number, just a constant. So it'd be 1/2 K1x squared from 0 to h, right? That would be the amount of area under this pretend f function. Okay, and we know that's the steepest it could go up, right? So that's the most area there could be under there. All right, so we plug in our h, we get 1/2 K1 h squared, and then minus, then you plug in a 0, of course you get 0. So there's the area under our pretend function. That'd be the most area we could possibly have. And then what would a left rectangle look like? What would a left rectangle look like in this function? Would it be 0? Remember I said we're going to make it easy and we're just going to start it at the origin, okay? So our one left rectangle here would actually have an area of 0, okay? So what's my amount of error? My amount of error would be my area minus my left rectangle. That would be 1/2 K1H squared, of course, minus 0 again. Well, that's just 1/2 K1H squared. Now we're gonna come back to that in a second. We're gonna go back to that in a second. Let's do a right rectangle. What would it, while we're at it, because left and rights are pretty much determined by K1, right? They're pretty much dependent by the steepness. So what would be one right rectangle here? It would be f of h, right? And my pretend f, right? My worst case scenario. So it'd be f of h times a width of h, correct? So height of f of h and a width of h. Okay, now what's f of h in my pretend f here? K1h, and then times my width, which is h, so that would be K1h squared, right? Correct? So my amount of error would be I minus R sub n. Now again, this is just for one subinterval. Okay, so it's not for all n subintervals, just in one. Would be what? It'd be 1/2 K1h squared minus my right, so it's my I, my total area, minus my right rectangle, which is K1h squared. Now what's 1/2 K1h squared minus K1h squared? Now why is it negative? Right, but I mean in area-wise, picture-wise. Why did it come out negative? Because an over approximation versus an under approximation, right? The left was under approximation. Here's my actual area we're talking about of my pretend f, right? So left was an under approximation, and my right's an over approximation, right? But notice how they're, so otherwise they're the same, right? Otherwise they're the same. So we'll just ignore the negative, because normally what do we do for our error? We put bars around it, right? Normally we put bars around it. And so that would just be plus anyway. So it's the same thing. So what we have just learned, and what we can now write, and I guess kind of out of room here, not really. So up here I could write I minus L sub n has got to be less than or equal to, now again, this amount of error right here is the max error, right? Because it's a worst case scenario, because I found my K1, I found where my function f had its steepest slope, and then I pretended that that function was that the whole time, right? So the amount this represents is the most error I could have. Now, let's rewrite it instead of h. What's another name for one width? Delta x, and what's a little formula for delta x? B minus a over n. B minus a over n, right? B minus a over n. Okay? So, let's rewrite this as 1/2 K1 and then B minus a over n all squared. Correct? And now let's go ahead and square that out. And then the 2 would be on the bottom and the n squared would be on the bottom. So I'd have K1 B minus a squared over 2n squared. Now remember, that was only for one subinterval. Right? That's the amount of error in one subinterval. But how many do we have in general? How many subintervals? N subintervals. So take that amount of error and multiply it by n subintervals. And this n would cancel one of those n's. And if you look on page 387, you get exactly that as the formula. And the right would be the same thing. So it's not just magic where that formula comes from. And it depends on K1. It depends on the slope. And that, of course, will be the most important thing I have you do. On the quiz this week, you can use your calculators, but you'll have to show your work. You'll have to write out this formula. And I'm going to be especially interested in what you're writing here for K1, and I'm going to talk about how we're going to find that K1 value. Okay? All right. We'll do that here in a second. But first of all, let's talk about the midpoint trapezoid. Okay? So we're going to okay? So now, let's take, and we'll kind of rewrite this a little bit here. All right. So this time we got this function here, whatever, going from A to B. Okay, but we're just going to look at one width here. All right. And this is F. But now we're going to talk about midpoints and trapezoids. Now, what determines how much a midpoint in a trapezoid is off? Concavity. The more curved it is, the more a midpoint in a trapezoid will be off. And K2, F double prime measures that. So, same logic. We will go through here and find where F double prime has its largest value. That's when the curve curves the most. And let's assume the function, let's pretend that the function had that curviness all the time. So what we will do is we'll say, okay, we want a pretend function where F double prime is equal to K2 the whole time. We're going to call K2 the max of F double prime, and we don't care if it's concave up or concave down. Okay? That's just over or under approximation. So what kind of function would have F double prime as its K2? Well, it would have an F prime of what? If it had F double prime was K2 the whole time, it was that number the whole time, what would F prime be? K2x. And what would F be? 1/2 K2x squared. So we're going to pretend that our f of x is not that function, but it's actually 1/2 K2x squared. We're going to pretend it has that K2 curviness, which this curve would, all the time. We don't care about the plus c and the shift and stuff. Okay? So, again, what do we have to do? We have to look at what the exact area under this pretend function would be. So we'll go 0 to h, 1/2 K2 x squared. Yeah, it's a lot of algebra, but it's kind of interesting how this works out. I mean, it's very doable with simple antiderivatives and a little bit of thought process of how we're finding the worst case scenario. It isn't incredibly difficult to see how this could come about. So let's go ahead and do that. What's our antiderivative of that? Remember, 1/2 K2 are just constants. So 1/6 K2x cubed from 0 to h. You plug in an h, of course you plug in a 0, you just get 0. So it's going to be 1/6 K2h cubed. That's this, if we had this worst case function, this would be the actual area under that. Okay? Now, what would one midpoint rectangle look like? Well, let's do it over here. One midpoint rectangle, I'll draw it on this F, but it'd really be on my pretend F, right? What would that rectangle have as its area? What would be its height? F of 1/2 h times a width of h, right? The f of 1/2 h. Now my f is this function here. This is my pretend function, right? And so let's put a 1/2 h into there. So we'd have 1/2 K2, and then we'd have 1/2 h plugged into it, right? And then times an h, right? So that would be what? When you square that, that'd be 1/4 times that would be 1/8. 1/8 K2h cubed. That's what my midpoint rectangle would be. So the amount of error, and again, this would be the max error, because this area here, this I here, is this worst case scenario area minus the midpoint. So if I subtract those, so I minus M would be 1/6 K2H cubed minus 1/8 K2H cubed. Well, that's easy. I just need a common denominator. This would be what? 4/24 minus 3/24. So this would be 1/24 K2H cubed. Right? Now let's put our B minus A over N in for H. 1/24 K2, and then we'd have B minus A over N cubed. So cube everything, the K2 would be on top, the B minus A cubed would be on top, you'd have a 24N cubed on the bottom, and this is only the error in one subinterval, so I'd multiply this by N, and that N would change that to a squared, and sure enough, if you look on page 387, the formula for the error in a midpoint is going to be that right there. It's dependent on the second derivative, which is what K2 is, the max of F double prime, the most curvy that the graph could be. Okay? All right. Now, don't write this down. I'm just going to very quickly show you one last piece. I'm not going to go all the way through it, but the last would be trapezoid because it's a little different than midpoint. Trapezoid would be f of 0 plus f of h, and then times h, correct? Look like that, okay? And f of 0, of course, would just be 0. F of h should be this. So we just have a 1/2. We'd have h plugged into that, which would be another 1/2 K2. Wait a minute. Yeah, that 1/2. Then there'd be 1/2 K2 h squared, and then times an h. So we'd end up with 1/4 K2 h cubed. So what we'd have is 1/6 minus 1/4, right? We'd have I minus t. So 1/6 minus 1/4, well, that's 2/12 minus 3/12, that'd be negative 1/12. We don't care about the negative. So it'd be 1/12 K2 h cubed. So it'd be the same as this, except there'd be a 12 there instead of a 24. And again, look on page 387, and that's what you see. All right? So there are essentially three formulas. Left and right are the same. Midpoint and trapezoid are close to the same, except one's got 24 on the bottom, one's got 12 on the bottom. Now what's that tell you about the error of midpoint and trapezoid? Which one's less error? Midpoint. It's got a bigger number on the bottom, right? 24 is bigger than 12. A bigger number on the bottom of a fraction means a fraction's littler. So midpoint has littler error, or a littler max error than trapezoid. That's something we talked about earlier. Okay. So, that you do not need to be able to replicate, but I hopefully that sinks in a little bit in the sense of where the thought process is and where that comes from. Okay? So, back to this question here on this page. Am I going to have to, I'm going to have to get out the other eraser. These people can see. Uh-oh. I'm going to let you guys cheat. Using your calculators, I'm going to cheat too. All right. All right, so K1, max of F prime and K2. All right, so go ahead and get your calculators out. So if this was the problem now, and this was a problem on the homework, this was a problem on the quiz, let's say, I might ask the question is, find the, I think in your homework they call it a theorem 3 error bound. If you look on page 387, that box, it's called theorem 3. I mean, don't worry about that. But if they say find a theorem 3 error bound, they're talking about using these formulas, okay? For an L20, okay, an L20. So what you would do is you would go to your, well, you would first write down your formula. You would say, okay, I minus L20 is less than or equal to, and according to the formula, now I'm going to put an empty box right there for K1. And when I look at your quiz, when you work a problem like this, I want to see that written out because you're going to get a point for what's in that box, okay, what you used for K1. All right, what would be in the B minus A? 2 minus 0, and then that's squared. And then divided by 2 times what? What would go down here in the formula? You have to look up page 387. I don't have it up here. What is it? The bottom is 2 times. Yeah, okay, this shouldn't be this hard. Page 20, thank you. On page 387. Right, we've got a left and a right, they're the same formula. If I'm doing an L20, right, if we're doing the error for an L20, that means n's a 20. Okay, so this would be a 20 right down here. Okay? Alright, so well, what I meant was it should be as hard. I'm doing a lousy job of explaining it if no one can tell me what goes there. Alright, so what we got to do is here is K1. Okay, so on your calculator, here's how we're going to do this. We want to find the max of f prime. Okay? So, Wyatt, I would say, now, f prime, what's f in this problem? What's f in this problem? Right here, right? Sine of x squared. So we'll always have f, we'll always have a and b, and we'll always have our number of subdivisions if we're trying to find the max error that 20 left rectangles have. Okay, so now if it's an easy one, you can do the derivative in your head, fine. If it's a harder one, you know, let the calculator do it, that's fine. I'm going to let you use a calculator on the quiz fragment. There's certain things you have to be on your paper and you have to show, but the rest of it you can use your calculator for. So go ahead and go to your template there and get your derivative and do the derivative as sine of x squared. Even though it's a very easy one to do in your head, what the heck? Let the calculator do it. So we go ahead and do that, and you got that. Okay, now, here's what I would do. There's a copy and paste command. Arrow back up to this. Even though it's an easy one to type, go ahead and hit Control-C for copy. And I think it's under the menu also. But if you hit Control-C, you can copy that. Okay, now go to the graph screen. Go to your F1 and go Control-V for paste. I think you can find it under either the dock or the menu, one of those. You can find the copy and paste. Now, it takes a little while to graph, especially depending on what your window is. Now, these are just some little tricks I want to tell you for when we get to the quiz. And you'll need them on the homework, and hopefully by the time you get through the homework, because I'm not going to help you on the quiz. You know, where was Zoom? What was it? You know, okay, that's what the practice on the homework is for. So go to your window settings, and where do we want to look on this function? 0 to 2. So go in your window settings and set your X-min and X max to 0 and 2. Now, sometimes that's all you have to do. Yeah, just hit OK then, or hit enter. Okay. Now, sometimes that's all you have to do. Now, remember, this that we're looking at right now is f prime. But zoom fit is a nice thing. I mean, we probably wouldn't have needed to because we can already see the whole thing. But if you can't see the whole, all the y values, then do a zoom fit. Okay, now, what place on that graph are we interested in? We're interested in the maximum. I heard somebody say or min. We're interested in the max of the absolute value of that prime. Remember, if a graph had a max of 2 and a minimum of -4, what do we want for K1? 4. right? We're interested in the negative 4. We want 4. Because the absolute value of f prime would just take this graph and flip it up. Now, if you say, well, why didn't we just graph the absolute value of f prime? That's a great question. If you want to, in your F1, to avoid that, if that's confusing to you, when you go to graph it, don't graph f prime, graph the absolute value of f prime. And then everything will be positive for you. But I'm not sure you need to go to that much trouble. I think it's pretty clear that we got this max, and we got this min. Which one do we want? This one down here, right? We want this y value is what we want. Because remember, these y values are the slopes of f. And that's what we're interested in, the max slope. Okay, so what we want to do is, and now, you can do a couple things. You can just go to trace, and I think when you get there, it'll tell you when you're at the min. But why it's at the right, go ahead and trace now. Go ahead and just arrow down there. Okay, and I think when he gets there, it'll tell him that's the minimum. And everybody try it and make sure you get yours to do that. Okay? And you should be seeing 3 or 4 or 5 or 6 decimal places. If you're not, then you've got a setting you probably need to fix because we want to be able to see those decimal places. Now, another thing that Wyatt was doing was went to Analyze Graph. Go to that. You can do that as well. You can go over here to Analyze Graph, go to minimum, in this case, or maximum. Lower bound. On the left somewhere, hit Enter. Go to the right somewhere, hit Enter. It gives you that, then you can go grab it, drag it over where you can see it, and there is the number you care about. Now, we don't care about the negative, right? We want the absolute value. So, you've got to be able to do that. You've got to be able to graph it, get the derivative, graph it, get your window set so you can find that biggest value, positive and or negative, okay? In this case, we want that. Now the question is, what do I put in my box for K1? Do I put that number right there? Just what? Well, absolutely, yes. We definitely never put a negative in the box here. I mean, K1 and K2 are both positive values. Absolutely, okay. Remember what we're trying to do here. The concept is more, the mechanics of working it out is important, but the concept is really the key. We want K1 to be a value, a worst case scenario, the steepest slope, a number that the slope will never be steeper than. Will 3.58 be that number? No. Will 3.5? No. Will 3.587? No. Even if you write that whole number all the way out to the 1, no. Because there's probably another number after it. What do we need to do?
4.
4. I would actually say 4 would be technically correct. I would not want you to use 4 though. Technically correct. Couldn't I use 10? 100? 10 million. Exactly. See, but that's the concept I want you to get. You're right. We're trying to find a worst case scenario, a number that the slope will never be steeper than. 4, it'll never be steeper than 4, never be steeper than 100, never be steeper than 1,000,000. But we want the most useful one we can get, right? Or a reasonably useful one. And so there's no fixed number to round to, but just get a sense by how big it is. If it's 3.58, to me, rounding it up to 4 is too much. 3.6, I think, would be good. Better, I think, would be 3.59. You're using your calculators anyway, so it's not that big a deal. Let's do 3.59. Now, the answer you eventually get then will depend on what number you picked here. So when I grade them, obviously, I'm going to have to look. That's why I want to see what number you use here. Now, if that number would have come out 27.58, then I think rounding up to 28 would have been okay. Because, percentage-wise, you didn't go up that much. But if the number's 0.58 and you round up to 1, I mean, geez, you doubled the number. So to me, that is a big difference. So if it's 0.58 something, then I go out maybe a few more decimal places. You see what I'm saying? So have a little bit of a sense of what that number is. All right, so you need to be able to do that on your calculator, find that number, then you put this on into your formula, and now go ahead and go back to the calculator screen, Wyatt. So you put the 3.59 While you're doing that, I'll show those at home. Of course, that's no being this big. So we put the 3.59 in the box. We go ahead and we type that into our calculator. And we get 0.359. Okay, now tell me what that number means again. That's the max that our L20 approximation is off. Now, it comes to mind that we haven't even done L20. Well, here's where we use that little program to do an L20. Now, the problem might not even ask you to do L20, but in this case, to investigate this a little bit, I want to do that. So let's go, if you remember, we go to the book. One way, there's several ways to get it. One way was to go to the book. You could go to area, but let's do it this way. Let's go to the book over next to the 9, the library, or the catalog. Go to number 6. Under area, you had RAM. That was the program that would do all of them for you. That's probably a good one to use right now. So let's go ahead and just hit enter on that one. That was a Riemann approximation method program. You go ahead and that paste it in here for you. You could have just typed it. Hit enter. Okay, it's telling you to run the program. Go ahead and type, what are you going to type in there? Sine of x squared. We're going to type the actual function. We're doing an L20 here. From 0 to 2. And we're going to do 20 subintervals. And so our L20 is 0.840 43 or whatever. So that's 20 lefts. Now while I'm at it, well, we probably won't take time to do the midpoint anyway here, so it doesn't matter. But, all right, now, let's make sure we all understand what information we all just found up here. So here's an L20. How far off is the L20? And the only reason we know how far off it is we cheated and used our calculator to do it. And these programmers have programmed to do it. We still don't understand how they did that. We'll get to that here in a few minutes. But how far off is our L20? About 0.035. It looks like we're off about 0.035. What did our formula tell us? Well, why was it so much different than how far off we were? The formula is the worst case. The formula is, that's like that $10 million in my pocket example, right? This is a worst case. It may not be as useful as we would like it to be. But what it is a guarantee. The only reason we know we're only off by 0.035 is we had the calculator cheat for us and tell us what the exact answer was. But this is a guarantee. And so what I could do with that information is pretend I didn't know this. And I didn't have the fancy calculator to do it for me. You say, yeah, but we need the calculator to do all this. Well, not really. I wouldn't have wanted to. It would have taken a long time. But we could, every one of these things we could have done by hand. We could have done the L20 by hand. We'd have had to have a trig table to look up our sine values, but we could have done it. We could have found the max of f prime by hand. It wouldn't have been fun, but we could have. Okay? I mean, if our lives depended on it, and we had a day or two, we could come up with those things. Okay? And then we could say, well, okay, our L20, we know it's not exact. How far off is it? We could say, well, we know that our exact answer has to be somewhere between 0.840 plus 0.359 and 0.840 minus 0.359. Because we know 0.359 is the most we're off. So I could go 0.359 this way, 0.359 this way, and I would know my exact answer would be somewhere between about 0.5 and about 1.1. Now again, that's not as useful as we'd like, but it's a guarantee. And that's worth something. Okay? It's a guarantee that it's in there. Now, let's see what would be best. I'll tell you what let's do. Let's finish up with this and then we'll talk about the K2. because that's pretty much the same thing. So, what about a problem that said this? So let's just go right into this problem. How many, because this is what the calculator programmers needed to know. How many left rectangles are needed to be within 0.0005? That's the real question that we want to investigate here. How many left rectangles would we need to guarantee we're within 0.0005? Now, what's that mean to be within 0.0005? How many decimal places accuracy is to be within 0.0005? How many decimal places of accuracy? Think Newton's method. 3. How many zeros are there, right? Because what that's saying is when you do your exact answer minus your approximation, when you subtract those and you get 0, that means those were right. Those decimal places were exact because they subtracted and got 0. So this would mean 3 decimal places accuracy. So this is the question. How many left rectangles are needed to guarantee that kind of accuracy? Well, let's write it out. So I minus L sub n would be less than or equal to, here's our K1, 3.59. We already found that. Times 2 minus 0 squared, divided by what? 2n. We don't know n. But we want that to be less than or equal to 0.0005. Correct? All we have to do is solve this equation, this inequality right here. Now, we'll go ahead and do it on the calculator. We'll use the solve on the calculator, and I'm fine with that. I want you to write this out, then you can use the calculator to solve it. Now, you can see what's going to happen. We're going to multiply the 2n over here. If we were doing it by hand, we'd multiply the 2n over here, and we'd end up with n greater than or equal to, right? So that's telling us our number of rectangles have to be greater than or equal to this amount, right? So we'll end up with something that'll be this, okay? So let's go to the calculator screen and let's do a solve. So Wyatt's already got it going, so we're going to solve. Now, wait a minute. That n, when it turns bold like that, means it's being used. Well, remember our Riemann sum program, it's already using n for that. So that's not going to be good. So if you see the n light up, use something else. Not light up, but bold-faced. Now, should he use less than or equal to? Go ahead and do it this one time, and I'll show you. No, it'd be less than. Be less than or equal to. And then 3 zeros. Okay? So now when he hits solve on that, and notice he hit comma C, telling it to solve for C. He gets C less than 0. Of course, the number of rectangles can't be negative, so we can ignore that. Or C is greater than or equal to 14,360. That's the one we want. Now, if he would have just used an equals there, then he wouldn't have gotten this less than 0 part. It would just have said equals 14,360, which is what we want. Now, the thing you got to remember is, if you just use equal to, what if it would have come out 14,360.1? Well, this is greater than or equal to 14,360.1. Can you have 0.1 subdivisions? Can you have half a subdivision, part of a subdivision? No, you have to have a whole number of rectangles. So what would your answer be? How many left rectangles are needed? It would be 14,361. You would have to round that up if it doesn't come out a whole number. Okay? But so when you solved it, he could have done an equals instead of that. All right, 14,360. There you go. That's how the calculator programmers know. They can run through this formula of finding, and they can have the calculator, they can program the calculator to get all these values. Once they know what F is, and they know what A is, and they know what B is, and they know how accurate you want it to be, then they can plug all those things in and they can solve for n, and then it can run a program like a left rectangle or a Simpsons or something. It can run a program to do that many of them. And it's guaranteed, then it knows the answer that spits out is guaranteed to be that accurate. Now, look at this. This one takes 14,360 left rectangles to be within 3 decimal place accuracy. Okay? Now, if we did it for a midpoint, we won't take the time right now, but the midpoint would take way, way fewer than that because the midpoint's so much more accurate. Okay? Now, I want to give you some work time here in a little bit. So let's talk about what would be different if you had to do K2. There you go. Go ahead. 14,360. Okay, we'll wait. We'll wait for a while it. Somebody in the other class tried running this program with
Billy, wasn't it?
Yeah, Billy did. I don't know if she did 1 million or 100,000.
I think she did 100,000. She was talking about it.
It took like 6 minutes or something, or 6 or 8. Eventually, I think it did.
8 minutes.
I feel bad for the
Is that what you
calculator.
said?
Well,
It's like
it-
thinking really slow.
it used our old calculators. These are fast because our old calculators. We had a similar program that we ran, and somebody put in like 100,000 or something like that, and then overnight they let it. It ran overnight, and they brought it back, and it was still thinking. So it took quite a while. So the fact that Billy's did it in like 6 or 10 minutes or whatever means these are a lot faster. All right. What? Well, okay. Somebody else is going to have to be presenter now. That's it.
I'll get back to you on that.
Well,
Yay.
Wyatt will get back to us. All right, Chris. All right, so
Go to your calculator screen. Okay, go to your calculator screen. And what, or no, there I said again. Actually, I meant grass screen, but no, I really want calculator screen. So actually, I had 2 wrongs make a right. Stay on the calculator screen. And if we were going to do our midpoint, right? So you look at page 387, you look at the formula for midpoint. Oh yeah, midpoint has K2 in it. So now we're going to need the max of F double prime. So you're going to need F double prime. So go to your template for F double prime, and there actually is a derivative. That one right there with the 2 in it is your second derivative. So you can now type that in, sine of x squared. Get that. Copy and paste that then into your F1, right? I mean, this is how you would find your K2 value, the same way you found your K1. But you got to make sure and do the second derivative. You go paste that in. You don't have to do the rest of it, Chris, that's fine. But you go ahead and paste that in. You would do a zoom fit or go from 0 to 2. You would look at the high and the low, okay? See, it's not even look like it's on there anywhere. Or it is, yeah it is, but we can't see it all. So this is where the zoom fit would come in. Zoom fit, find that K2 value, and you would work it out. And if we wanted to know how many midpoint rectangles we needed, we could go through and we could do that. Okay? All right. So there you go. 8. Oh wait, we got. But this is probably past it, isn't it? This is out here like 2.4 something, I think. So even if you tried to find that, I don't think it would. So 8.29, see, to me, you could go 8.3 and you'd be just fine with that. You could use 8.3 as your K2 value. And see, and I'll be looking at that. If you use, if we have a problem that's this and you use 8.29, you're going to miss it. Now, I know that's really a technicality because clearly the second derivative, 8.29, would be more than enough. Okay? But again, what I really want you to understand is we're picking a worst case scenario. We're picking a number that we know guaranteed there is no number bigger than that in this second derivative. And that's why I want you to round it up.
If you do it at 2, it's technically nothing.
Is it
Yeah.
at 2? Go ahead and trace it 2 there, Chris. See, the window looks a little different. In our old calculators, when we did a zoom fit, if we put in 0 to 2, I mean, it would just stick right there. You could not see past 2. But this one seems to give us a little wiggle room on each side. So you may need to check your endpoints. Yeah, see, so that's a little bigger. See, so on one like this, I would, like 10.8016, I would not go 10.9 on that, I don't think. I mean, that'd be okay. But you go 10.81 to me, 10.81. If you went 10.9 and I saw that, and you know, that would probably be acceptable. But
What do you want to go out as far as you can and just increase the last number?
yeah, I mean, you could go out 6, 7, whatever. Then yeah, no, you could. I mean, that would be more useful, wouldn't it? The less you have to round it up for whatever number you have, the better. So if we would have done that on this one instead of 14,360, we might have come up with 12,870. So, you see what I mean? So when we say, now, and I'm sorry, I'm glad you said that because I forgot to mention this. When we say it takes 14,360 left rectangles to get 3 decimal approximation, does it really take 14,360 to get 3 decimal places? Remember, we got this number by the worst case scenario. Chances are 14,360 rectangles will give you like 6 decimal places actors. Maybe 7, I don't know.
You got
But that's the key. That's the key, we don't know. What 14,360 does do is guarantee that you'll have 3 decimal place accuracy. But probably less than that, we'll give it to you. Okay, so it's important. It seems like those are subtle differences, but it's important to understand that.
3 decimal places.
All right, it came out?
3 decimal places. As soon as you get to the 4th decimal place, it's wrong. Then
Or by less than 0.0005.
Okay, so, yeah. And so the exact answer we had already said was 0.804
Calculation.
something, and we had, somewhere we had it. Okay, so that's good. Oh, here it is down here, 0.80477. So it's within the 3 decimal places like this. Okay? And actually it wasn't more than that, was it? It really wasn't accurate out into the 4th.
No.
So we didn't get extras. Okay? But if he would run it again with 13,000 or whatever, if we would have made this number 3.58, and went out a few more decimal places, we might have been able to lower this number a little bit and still get 3 decimal place accuracy. Okay? All right. So your homework is the second line there. You got the last 30-some minutes here to work on that. Okay? I'm sorry, not the 6.2 line. 6.2 line. Okay, and you're going to be doing some of this. Now, we had asked the question last week, will this area program work when we're in press to test mode? I haven't quite been able to get that to work. I can send it to you in press to test mode, and you can have it, but the refresh libraries part doesn't work, and then it's not available. But to be honest, I'm not sure that really matters. So if you think about everything we've just done here, you have to write this stuff up, use a calculator screen. The only time we went to our calculator for the program is when we wanted to know what L20 was, and that was just out of our curiosity to see how close we were. So if I can't get that to work, I just won't ask any questions because what kind of question would that be anyway? What's L20? And you get your program out, you run it, whatever it says, you write it down. I'm not sure that's much of a quiz question anyway. I guess it's an easy one. That's it'd be it's a great test question.
Get the test out of it.
Okay, I forgot who I was talking to. All right, but so unfortunately, we may not have any of those questions on the quiz if we can't use that program that way. But to be honest, I probably wasn't going to ask a question like that anyway. But what I might have said is, how far off is an L20 from the exact answer and something, and you would have needed it to do the L20, but I'll just leave that part of it out. Or else I'll tell you.
I'm going to be back tomorrow, so how much is the package?
Oh,
None of it.
yeah.
All of it.
Yeah, that's a good question, because tomorrow we're going to go over homework.